refer to the sheet titled Electromagnetic Induction, sheet 2. By this time you would have attempted a few problems, and let's go through these problems together then, right? Sheet 2. So the first problem of the sheet is about an inductor L having a resistance small r. Together they are referred to as a solenoid. With a resistance R connected like this, a battery of EMF E, there is a switch S. This is the state of the circuit prior to t equal to 0, and the circuit has accomplished its steady state conditions. Prior to t equal to 0, the circuit was activated with the switch on, and the circuit had reached its steady state conditions. Which means, just about at t equal to 0, on the transition of a change, well, up to t equal to 0, you can imagine that this behaved like zero resistance, and this EMF dropped across this, and the current through this branch would have been E by small r. Yes or no? Prior to t equal to 0, under steady state conditions, the current through this would have been E by small r. There would be energy in the magnetic field associated with the inductor. The energy in the magnetic field associated with the inductor would have been half L I naught squared. Right? The current in this branch would have been E by capital R, and the current through the battery would have been E by small r plus E by capital R would have been the current through the battery. Now, at t equal to 0, this switch is opened. Deactivated. Once that is done, the current in the resistance will die out instantly, right? That's the property of a resistance. The current in the resistance capital R will die out instantly, but the current through the inductor will decay gradually, right? It will now begin to circulate through this with an initial current I naught. There would be decay of current through this LR circuit, right? Now the current as a function of time then is going to be I naught, which is E by small r into 1 minus e to power minus t capital R plus small r by L, right? That's the current time characteristic for t greater than 0. For t greater than 0, this is how current time characteristic look. Clear? The amount of heat generated in the solenoid. So eventually, this current I naught will decay, right? There would be joule heating across small r, and there would be joule heating across capital R. Whatever joule heating takes place across small r is the energy consumed by the solenoid, right? Now this total amount of energy U naught gets delegated between small r and capital R, proportional to their resistances, right? So the energy which is consumed by small r, that is the solenoid, is going to be the total energy into small r by small r plus capital R. Yes or no? Do you realize why? Not sure about this? Hey, UR divided by U capital R will be small r by capital R, isn't it? Will be proportional to the resistance. Energy lost across this plus energy lost across this. And UR plus U capital R would be U naught. So I can write this equation as UR by UR plus U capital R is R divided by R plus capital R. And UR plus U capital R is the total energy consumed, which is U naught. Which is U naught. Yes or no? This is U naught. So U across small r would be U naught into small r by small r plus capital R. U across capital R will be capital R by small r plus capital R into U naught. U naught is the total amount of energy dissipated as joule heating across small r and capital R, proportional to their respective resistances. Clear? Is that okay? Let's look at the next problem. Okay, is there any other part to the problem? No. Can I wipe this off? Now in the next problem, problem 2, we have two inductors L1 and L2. Battery of EMF E with a resistance capital R and say a switch here. We want to be able to find the current through L1 and L2 as functions of time, Now, this circuit is equivalent to a L, which is two inductors in parallel, L1, L2 by L1 plus L2, with a battery of EMF EPSA, switches, right? And a resistance, Now, the current through the battery as a function of time, it's a typical LR circuit. So current is going to be E by R into 1 minus e to power minus t into R by L. That's current as a function of time through the battery, right? Now this current I gets partially delegated to L1 and partially to L2, right? In a manner that the drop across L1 is the same as drop across L2. Now what's the drop across L1? L1 di1 dt. What's the drop across L2? L2 di2 dt. So which means L1 di1 dt is L2 di2 dt. I can cancel dt, and if I integrate, I end up getting L1 I1 on integrating is L2 I2 is what I end up getting, right? So which means I1 divided by 1 by L1 is I2 divided by 1 by L2. Each is sum of the numerators divided by sum of the denominators. Sum of the numerators I1 plus I2 is I, isn't it? I is I1 plus I2. So this is I, which is known as a function of time, the total current through the battery, divided by 1 by L1 plus 1 by L2. So then this and this will give me I1 as a function of time, this and this will give me I2 as a function of time, because I is known as a function of time. So the current through the two inductors would be then available as functions of time, I1 and I2. Is that okay or not okay? Let's look at problem 3. Simple, right? This. L1 I1 is L2 I2, so I1 by 1 by L1 is I2 by 1 by L2, right? And this comes from here. I cancel dt and I integrate both sides, so L1 I1 is L2 I2. And then from here, I1 by 1 by L1 is I2 by 1 by L2. Number 3. So in problem number 3, we have a very long current carrying wire, carrying current I. And there is a rectangular wire frame. A, B, C, D. This is a rectangular wire frame, A, B, C, D, having an inductor L here, and a connector, a movable connector which can move with respect to the wire frame with a resistance capital R. Designate this as PQ. PQ is the connector. The dimensions are, this is A units and this is A units. The wire frame moves up with a velocity v. The wire frame moves up with a velocity v, and the connector moves with a velocity 2v. The connector moves with a velocity 2v. And this length is known to be small l. And this is the state at time t equal to 0. We want to find the current through the inductor L at an instant when PQ just loses contact with the frame. That means when P coincides with A and Q coincides with P. That means at what instant of time? See, L by V. See, because the relative velocity of PQ with respect to the wire frame is V. So L divided by V is the time when it loses contact. We want to find the current through the inductor at time t0. At an instant of time t0, we want to be able to find the current through the inductor. Now, see, there is motional EMF in PQ. PQ is moving. How do I calculate the motional EMF in PQ? This is the current I. This is PQ, right? This has a velocity v. So if I look at an element here at a distance x from this current carrying wire and of length dx, right? Then there is going to be a motional EMF bv into dr, right? V is like this, 2v, right? B is into the plane of the board, so 2v cross b would be this way, right? So there is going to be a d epsa that it contributes, So the d epsa that this contributes is going to be b. The b at this point is going to be mu naught I by 2 pi x. Into velocity 2v, bv into length L, which is dr, dx. That's the, yes, confusion. Yes. Relative velocity is v. See, you're right. Actually, I'll tell you. This is motional EMF. There is motional EMF also across CD. So we'll subtract that. You know what I'm saying? We'll subtract that. What I want to say is, this is just across PQ with a total velocity 2v. Then there is going to be EMF, motional EMF across CD, which would be in this sense, and that would be subtracted. So that will be the net EMF available in the loop. So across PQ, it's going to be this only. Right? Across PQ, it's going to be this. Across CD, there is going to be another motional EMF, and the net EMF will be the difference of the motional EMFs across PQ and CD, which is which will then effectively turn out to be V, right? So that's emotional EMF across PQ. Sum of all of this, where X runs from A to 2A, right? So, which is mu naught I by 2 pi X log 2 into 2V. Mu naught I by 2 pi, mu naught I by 2 pi, 2V into log X, which is log 2A by A, which is log 2, right? That's the motional EMF across PQ. And the sense of this motional EMF across PQ is this. EPSA across PQ is directed this way, right? And then there is going to be EPSA across DC, which would have this as the polarity, right? And PQ and DC are the same, except that instead of 2V, you will have V for DC. Yes or no? So EPSA across DC is the same as EPSA across PQ, except that this 2V would have to be replaced by V. All other calculations will remain the same. So that's going to be mu naught I divided by 2 pi log 2 into V. That's the motional EMF across DC. And do you realize that the net EMF would be like this? EPSA PQ minus EPSA DC is going to be the net EMF in this loop, right? So this will serve as an effective battery. EPSA in the circuit, which would be this way, which is EPSA PQ minus EPSA DC, which is mu naught I by 2 pi log 2 into V. That's the motional EMF, net motional EMF, right? So then this is a typical LR circuit, with this being the EMF of the effective battery. Then the growth of current in this LR circuit is going to be, I will be EPSA, which we have already computed, divided by the resistance R into 1 minus e to power minus t into R by L. So now we want to find current I at t equal to t naught. So just plug in t equal to small l by v, you will get the current I naught at an instant when PQ loses contact with the wire frame. Right? Problem number 4. Is a circuit of this kind. Resistance R equal to 10 ohms. There is a key K1 here. There is a capacitance C1 which is 2 microfarad. Another capacitance C2 which is also 2 microfarad. There is an inductor L which is 0.2 millihenry. There is a key K2 here. Now, so very clearly there are two entities in the circuit. There is a RC circuit. The upper loop is an RC circuit which is activated and has reached steady state conditions. There is a lower loop prior to t equal to 0. It's not active, it's deactivated. This key is open, right? Now, let me examine the state of the circuit upon having reached steady state conditions. Let me examine the state of the circuit prior to t equal to 0, when it would have already reached steady state conditions. Now, what would be the current through this loop? 0. Why? Because the capacitors offer infinite resistance. So now there is no current, which means what's the drop across this resistance? 0. That means this 20 volts will drop across these two capacitors, and since they are identical, it will drop across them equally. There is going to be a 10 volt drop here, there is going to be a 10 volt drop here. That means the charge on this is going to be 20 microcoulombs here, minus 20 microcoulombs here, 20 microcoulombs here, minus 20 microcoulombs here. That's a steady state charge distribution on the two capacitors in the upper loop. Yes or no? Right? Now, suddenly this switch is deactivated. And this one is enabled. So now the upper circuit is inactive, passive. The lower circuit comes into action. At time t equal to 0, the lower loop gets activated, and it's a typical LC circuit with the capacitor having an initial charge Q0 equal to 20 microcoulombs, right? And then what would happen is there would be a current driven through the loop, which would be sinusoidal in character. The charge time distribution on the capacitor would be sinusoidal in character. Energy would oscillate between energy in the electrostatic field of the capacitor and magnetic field of the inductor. It will shuffle between the, with the total energy at all times remaining Q0 squared by 2C1, right? Now, the charge time variation on the capacitor is going to be Q equal to Q0 cos omega t, because at t equal to 0, Q was Q0. Right? That's going to be the charge time variation on the capacitor subsequently, where omega is the angular frequency of oscillation of the circuit and would have a value 1 by root LC1. Right? The current, say minus dq dt in this case, is Q0 omega sin omega t. Right? That's the current in the circuit as a function of time. Now what we are seeking to do is, okay, so the first part of the problem, find the angular frequency of oscillation of this LC circuit. This is an LC circuit, it's going to be this, 1 by root LC1. We want to then find the first instant t when the energy in the inductor becomes 1/3 the energy in the capacitor, right? So we want to find that instant when the energy in the inductor is 1/3 the energy in the capacitor, right? Now at any given instant when the current is I, what is the energy in the inductor? Half of L into I squared, which is Q0 squared omega squared sin square omega t. Is 1/3 Q0 squared by 2C1, that's the energy in the capacitor, Q squared by 2C1, Q squared by 2C1. So Q0 squared cos squared omega t by 2C1. Yes or no? This gets cancelled, Q0 squared gets cancelled. Now realize that omega squared L into C1 is 1. Omega squared L into C1 is 1, right? So this omega squared L into the C1 turns out to be 1. So that gives me tan omega t is 1 by root 3, right? T then, omega t then is pi by 6, pi by 3, pi by 6, yes, pi by 6. T then is pi by 6 omega. T then is pi by 6 omega. Omega is 1 by root LC1. Yes or no? At this instant of time, the energy in the inductor will become 1/3 the energy in the capacitor. Yes. Charge on the plates of the capacitor at that point of time? Well, omega t is pi by 6. So plug in omega t as pi by 6 cos 30 degrees. So q naught root 3 by 2. Q naught root 3 by 2. Omega t is pi by 6. So q naught cos 30 degrees. So that means q naught into root 3 by 2 would be the charge on the capacitor at that instant of time. Clear? Let's look at problem 5. I hope you were able to solve this independently also, right? Pretty simple problem. Now, problem number 5. There is an inductor L1 having a resistance R1. There is another inductor L2 having resistance R2. There is a galvanometer here. Okay. Now, what the problem seeks from us is, when this switch is activated, at all times the galvanometer will show zero deflection. What should be the condition connecting L1, R1, L2, R2, R3, R4 such that the galvanometer will show zero deflection at all times? Now, galvanometer showing zero deflection at all times means no current through the galvanometer. That means the potential here must be equal to potential there at all times, right? That means this point and this point must be at the same potential at all times, right? Now, and that should happen starting from t equal to 0 up to steady state conditions. This is what is being, okay. Now, suppose the current here at an intermediate instant is I1 and the rate of change of current is di1 dt. At the same instant, let's say the current here is I2 and the rate of change of current is di2 dt. Now, this point and this point are at the same potential, electrically the same, and these 2 points are also electrically the same because you don't expect any current through the galvanometer. So that means the drop across this must be equal to the drop across this, right? The drop across, what's the drop across this? Drop across the inductor L1 di1 dt plus I1 R1 must be equal to L2 di2 dt plus I2 R2, right? So the drop across the L1 di1 dt plus I1 R1 must be equal to L2 di2 dt plus I2 R2. That's one thing. That will happen always. And now when current I1 comes to this junction, it will go undeviated to R3. When current I1 comes to this junction, it will go undeviated through R4. I2, right? Now, these two are electrically the same. These two are electrically the same. So the drop across this must be the same as drop across this. What's the drop across this? I1 R3 is I2 R4. Now, as far as the physics of the problem is concerned, it's just about this much. We've actually solved the problem. We now have to interpret the whole thing effectively, right? The first thing that we can do is between I1 and I2 we can eliminate one of them. Say I can eliminate I2. This I2 I can write as I1 R3 by R4. I could do that. So that I have only I1 to deal with. Let me eliminate one of them. Let me write I2 as I1 R3 by R4 in this equation. Right? When I do that and transpose things on one side, then dI1 dt into L1 minus L2 R3 by R4 equals I1 into R3 by R4 into R2 minus R1 is what I get. Yes or no? I hope you realize what I've done here. I've just replaced this I2 by I1 R3 by R4 and transposed this term on this side and this term on this side, replacing this I2 by I1 R3 by R4. This is all that I've done here. Clear? Okay. Now, at time t equal to 0, imagine the two extreme instance. At time t equal to 0, when the circuit was just about activated, current I1 was 0. Right? At time t equal to 0, this offers infinite resistance. Current I1 would be 0. But rate of change of current will not be 0. There would be growth of current, but the current itself will be 0. So at time t equal to 0, the current I1 is 0, but dI1 dt is not 0. dI1 dt is not 0. Yes or no? Right? Do you all understand this? Now come to this equation. This is 0. That means the right hand side is 0. That means this into this is 0. But dI1 dt is not 0. So this must be 0. Yes or no? I hope you understand what I have said. I1 is 0 at time t equal to. This is true for all instants of time. T equal to 0 as well as t equal to infinity. At t equal to 0, I1 is 0. So right hand side is 0. But dI1 dt is not 0. So which means this must be 0. This equal to 0 means what? L1 by L2 must be R3 by R4. Right? I hope all of you understand this part. So that's t equal to 0. Let me imagine the other extreme. Steady state, t very large. Now, when t is very large, steady state, that means there would be no further growth of current. dI1 dt will be 0, but I1 will not be 0. Right? I1 will not be 0, but dI1 dt will be 0. Yes or no? Right? So, if dI1 dt is 0, left hand side is 0. I1 is not 0. So that means this must be 0. If this is 0, it would mean R3 by R4 must be equal to R1 by R2. So R3 by R4 must be equal to R1 by R2. This is what must be met. This is the physical requirement. L1 by L2 equals R1 by R2 must be equal to R3 by R4. Clear? Number 6, very simple, 4 ohm resistance, 5 millihenry inductance, 6 ohm resistance, So this switch was closed at time t equal to 0, and we want to find the current through this key at t equal to 10 to power minus 3 log 2. Very simple. See, this is our RC circuit in which current flows as a function of time, right? So in this case, what is I as a function of time? I equal to I naught. What is I naught? 20 divided by 5, 4, isn't it? 20 divided by 5, 4, e to power minus t divided by RC, 5c, right? I'll write RC, we'll adjust, that's say I1 as a function of time. And then this is a typical LR circuit in which there is I2 as a function of time. What is, so this is I1, what is I2? I2 is epsa by R, that means 20 divided by 10, which is 2. 1 minus e to power minus t into L divided by this R, right? This is R1 for this, say, minus t into R1 divided by L, where what is R1? R1 would be 10. So all that you need to plug in is t equal to 10 to power minus 3 log 2 here, and t is 10 to power minus 3 log 2 here, and find I1 plus I2 at that instant of time. That's all, isn't it? Plug in the value of t, 10 to power minus 3 log 2 in both these equations, and obtain I1 and I2. Clear? Simple, isn't it? So see, this log 2 will make sure that the exponential goes away. E power log 2 would be 2, and the minus will make it half, and 10 to power minus 3 will make this milli f, isn't it? So it's not going to be. Number 7, a coil of inductance 1 Henry and negligible resistance is connected to a source of supply whose voltage is given by 40 volts. That means varying with time. If the voltage is applied at t equal to 0 and switched off at t equal to 4 seconds, we want to find the energy stored in the coil. So the coil at any given instant of time will have drop 40 volts, right? Because this is the source which appears entirely across the inductance. So that means across the inductance, if I is the current at any given instant of time, then L di dt would be 40. That's what happens across the inductance, right? L is 1, so di dt would be 40 dt. Integrate both sides. At t equal to 0, current was 0, right? It offered infinite resistance. And at time t equal to t, let's say t equal to how much? T equal to 4 seconds. Let's say current became I naught. So you would know I naught from this. This will be 2t squared. T runs from 0 to 4. So I naught is known. So the energy stored in the inductor would be half of L I naught squared. I naught is known from these considerations at t equal to 4 seconds. Simple, isn't it? A circuit contains an inductance. A circuit contains an inductance L, a resistance R, and a battery of EMF epsa. The circuit is switched on at time t equal to 0. The charge flowing through the battery in a time constant tau. What is tau for a LR circuit? L by R. L by R is tau. That means in a time t equal to tau, what is the charge flowing through the battery? So all that you need is current at any given instant of time. That's going to be epsa by R, 1 minus e to power minus t into R by L. That's current at any given instant of time t. The total charge in a given time would be integral I dt. T runs from 0 to tau. That's going to be the total charge flowing through the battery. Where tau is what? Tau is L by R. So easy integration with this limit will give you the total charge flowing through the battery in a time equal to one time constant tau. Number 9, the smallest time in which the charge on the plates of the capacitor will become 0, I told you, is pi by 2 omega. Huh? Yeah, T by 4. Right. So omega is 1 by root LC. Omega is 1 by root LC. So pi by 2 omega is a result which I gave to you in the last class. Simple, right? All right. We want to find the potential difference between A and B when the current passing is 5 amps. Okay, so the first part of the problem, when the current passing is 5 amps, there is drop across this, which is 10 volts. Plus, what's the drop across this? 0, because dIdt is 0. What's the drop across this? Minus 10 volts. That makes it 0 volts, isn't it? When a steady current of 5 amps is passed, the drop across the inductor will be L dIdt, which is going to be 0 because dIdt is 0. The drop across this is going to be plus 10 volts. The drop from here to here is going to be minus 10 volts. So that makes it 0 volts. That's the first part of the problem. In the second part of the problem, current passing is 5 amps and it's increasing at the rate of 100 amperes per second. It's increasing at the rate of 100 amperes per second, right? Then what's the total drop? Then the total drop from A to B, the drop across the resistance will still be 10 volts. Plus L dIdt would be the drop across this. So 10 into 10 to the power minus 3 Henry into dIdt, 100. That's the drop across this. And the drop across this is going to be minus 10. So the drop across the whole thing would be this much, 1 volt. 1 volt would be the drop. Yes or no? There is a 10 ohm resistance. There is a 10 millihenry inductance. There is 5 volts like this. (100 ohms like this). Under steady state conditions, we want to find the current through the 10 ohm and the 100 ohm resistance. Under steady state conditions, we want to find the current through the 10 ohm and the 100 ohm resistance. Okay. See, under steady state, this offers 0 resistance. That means all the current will flow past this only. There would be no passage of current through this, right? And the current then would be 5 by 10, which is half amps. Yes or no? Because this would be ineffective. If this is behaving like 0 resistance, then the entire current will pass through this. This part of the circuit would be ineffective. That means the current through this is going to be 5 by 10 amps. Right? So this entire current passes through this and the 10 ohm and 0 current through this. That is what happens under steady state conditions. Clear? The energy stored in the capacitor under steady state conditions. See, under steady state conditions, this E volts will drop across this, half CE squared. Right? Half CE squared. Energy stored in the capacitance is going to be half of CE squared. We are maintaining this E volts. No current through this, half CE squared. Right? Is going to be the, okay. Energy stored in the inductor element. Yes, and what is I through the inductor element? There is E volts drop across this. So the current through this is going to be E by R, because this behaves like 0 resistance. And therefore, the energy stored in the inductor is going to be half of L into E by R whole squared. Very simple. Oh, 13 is unnecessarily a repeat. number 16. All the best, huh? Problem number 16. Which is a resistance R, inductance L, another resistance R, a capacitance C, now in this circuit they say the current in the battery rises instantly to its steady state value E by R. We need to show that R must be square root of L by C if this happens. Now a funny little thing, you know, how can it rise instantly to its steady state value? Okay, look at two parts of the circuit. This is current I1 at any given instant of time, this is current I2, and this is current I flowing through the battery, which is going to be I1 plus I2. This loop is a typical LR circuit. So I1 as a function of time is going to be given by what? E by R into 1 minus e to power minus t into R by L. Clear? I2. This part is a typical RC circuit, right? This is going to be given by E by R e to power minus t by RC, right? Absolutely, you're right. The current I through the battery is going to be I1 plus I2, which is going to be E by R 1 minus e to power minus t into R by L plus e to power minus t by RC. Now what they want to say is that current is time independent. That means right from the word go, it does not care about the instant of time. It's going to be the same current at all times, and therefore steady state from the word go. This is what is now. If it has to be independent of time, that means these two terms must cancel each other. Yes or no? For these two cancel each other, this part must be equal to this part. That means R by L must be 1 by RC. Yes or no? R by L must be 1 by RC, then it will become time independent. Right? For it to be time independent, then the requirement is R by L is 1 by RC. R therefore would be root L by C. Right? So here we have a 100 microfarad capacitor and L equal to 10 Henry. Another switch, let me call this C1, 900 microfarad. This S1, let me call this S2, let me call this C2. Now, initially, this capacitor is charged to 100 volts. This capacitor is charged to 100 volts. That means the energy in this capacitor U1 is half of 900 into 100 square microjoules. Yes or no? 10 to the power 6 microjoules. 4.5 into 10 to the power 6 microjoules. Yes or no? Right? That's the energy in this capacitor. Now, what is done is, for T1 seconds, this switch is activated for T1 seconds. For T1 seconds, this loop is made active. Right? After t1 seconds, this is opened up. After t1 seconds, this is opened up. And then, at the same instant, this is activated. At the same instant, this is activated. And for t2 seconds, this part remains active, this is inactive. Right? Now, t2 seconds from this point, it is found that this capacitor is charged to 300 volts. This capacitor is charged to 300 volts. In t2 seconds of activation of this causes this capacitor to get charged to 300 volts. What's the energy in this capacitor? Half CV squared, half of 100 into 300 squared. These many microjoules, 4.5 into 10 to the power 6 microjoules. Right? No, which is the same as that. Which means the following must have happened. We want to find the smallest values of T1 and T2 for which this could have happened. What must have happened is the following. When this was activated for T1 seconds, the entire energy, electrostatic energy, got converted into magnetic energy here. Now this opened up. Now there was no energy remnant here, right? And then for T2 seconds, this part was made active. And the entire energy that this contained got translated into electrostatic energy for this, right? Now the time it takes, that means in T1 seconds, all electrostatic energy of this loop got converted into magnetic energy. In T2 seconds, all magnetic energy of this got converted into electrostatic energy of this, right? T1 therefore, see, for this part of the loop, omega 1 is 1 by root LC1 for this LC loop, right? Therefore, T1 must be pi by 2 omega 1. I told you this, right? This is the time it takes for the energy to completely shuttle from electrostatic to magnetic or vice versa, right? And the omega for this loop is 1 by root LC2. And in T2 seconds, entire magnetic energy got translated into electrostatic energy. So T2 must have been pi by 2 omega 2. These are the smallest values of T1 and T2 for which this could have been obtained or accomplished. Got me? There is a rod which is hinged at A, say. This is the vertical direction, G. And there is a horizontal magnetic field to which this entire thing is exposed. The rod is of mass m, length L, and can rotate in a vertical plane about O. So call this O. A horizontal magnetic field is applied. We want to find the maximum electric field that ever can be produced inside the rod. Now for the rod, see, while it swivels about O, it develops an omega, right? Now if I look at an element here at a distance x, if I look at an element dx, right, there is going to be the velocity of this element is going to be omega x, right? The EMF that is generated in this element, d epsa, is going to be bv into dx, is going to be the EMF contribution of this element, bvr. The electric field is going to be d epsa dx. The electric field is going to be d epsa dx, isn't it? Rate of change of potential with x. So the electric field at any given x is going to be d epsa dx. Rate of change of potential, which is bv, right? Where v is x omega. V is x omega. Now, one thing, for a given omega, E will be maximum when x is L. Maximum possible value of x is the length of the rod. So for a given omega, the electric field will be maximum when x equal to L. That means at this end of the rod, right? Now, so at all times, the electric field, maximum electric field will be witnessed at this end. Let me call it the end A. Now, when would omega be a maximum? Omega will be a maximum when the rod becomes vertical, When the rod becomes vertical, omega will be omega max. So the maximum electric field will be B into x equal to L into omega equal to omega max. When is omega max? When the rod becomes vertical, the entire potential energy gets converted into kinetic energy of rotation about O. So which means, what is omega max? How do I obtain omega max? Half of, when the rod becomes vertical, when the rod becomes vertical, omega will be omega max, right? And to obtain omega max, half of I about O. I about O is 1/3 ml squared. Kinetic energy, omega max squared in the vertical state. And where did it come out of? It came out of loss of gravitational potential energy, mg into L by 2. Yes or no? I hope. Why L by 2? Because the center of mass was originally here, and now this is where the center of mass is, L by 2. So loss of gravitational potential energy gets converted into kinetic energy of rotation. Right? So you know omega max. So E max would be B into L into omega max. That's going to be E max. E max is going to be B into omega max obtained from here into X max, which is L. Got it?